Okay, well, let's get started then. Welcome everyone to our May meeting. Thank you all for turning up. We've got a very exciting meeting today. We have a great friend of the Society, Dr. George Seabroke from MSSL, UCL. We've done a lot of outreach work together. In fact, even appeared on TV together to some extent. So lots of fun times. George is Principal Research Fellow at the MSSL, UCL. He started working on Gaia straight after his PhD, Open University, and modelled Gaia's charge-coupled devices before moving to MSSL in 2010 to work on the Radial Velocity Spectrometer. Having worked exclusively on Gaia for 15 years, you're also simulating instrumentation for future missions, apparently. So we should have a very interesting talk. Anybody who doesn't know, we, as a society, took some pictures and did some interesting things with Gaia that I'm sure George is going to go into. Yeah. So please welcome George Seabroke.
Well, great. Yeah, well, thank you very much for the introduction, and yeah, thank you very much for the invite to be here. I think it was back in 2017 I was last here.
Yeah.
So quite a lot has changed with Gaia since then. So I will give you an update. So first of all, I'll talk a little bit about what Gaia's trying to do. So that's the history of astrometry. So astrometry is the science of measuring the positions of stars, and this is what Gaia's all about, basically. So on this plot, we've got arc seconds on the y-axis against year on the x-axis. So to give you your bearings a little bit, a full moon subtends half a degree. So that's 1800 arc seconds. So that's at the top there. So you'd hope that you'd be able to do star positions better than that. And indeed, this is what this plot is saying, even back in 150 BC. And so as we go forward in time, I'm just going to jump to 1826. So it's an auspicious year for many reasons. So 200 years ago. But it was this chap here. So Francis Baily published a catalogue called the Astronomical Society of London Catalogue. So the Astronomical Society of London went on to become the Royal Astronomical Society. And he published this for nearly 3,000 stars. And he was basically a sort of an early Gaia in that he actually took other people's star measurements and moved them up to the modern epoch. So some of those star measurements that he'd took from other catalogues were quite old, and he recalculated their positions and published them in 1826. And it also happens to be the year that UCL was founded. So we're celebrating our 200th anniversary this year. So the reason I'm interested in Francis Baily is because he was born in Newbury, and I'm from Newbury. But when I was growing up, and I guess staggering past his birthplace on the high street, because the pub we used to go to was just next door, I didn't actually realise that he was from Newbury. And this blue plaque, which is on the high street in Newbury, was put up since I left. But you may know his name better from the Baily's beads fame. But actually, he wanted to be known for his star catalogue work, and of course, it's 200 years since his catalogue was published, and it's going to be Gaia's 4th data release is coming out later this year. And in fact, today was the day we've actually announced the actual date of that, and that's the 2nd of December. So it's also an auspicious day as well. So, and then so for this catalogue, he got the gold medal of the Royal Astronomical Society, and he was also the president many times. I think he holds the record for the longest time period of being president. And then it was in 1826 he wrote a paper describing the beads that you can see. So I haven't had the fortune to witness this. Maybe some people in the audience have. So Baily's beads are just before going into totality. The sunlight, the last bits of sunlight you see coming through the valleys between mountains on the moon. So he described that in a paper, and then that's how it stuck But for me, Francis Baily was a school actually that we used to play football against at primary school, and they always beat us. But anyway, so that's so because of the anniversary of his catalogue and the fact that I grew up in Newbury not knowing about him and then went on to become an astronomer, I'd like to do something this year or maybe next to celebrate his work. So I'm not sure what yet, but we'll watch this space. But of course, I got to do my own finding out about Francis Baily in the High Street. My children preferred Paddington, which is a bit further down the road. Of course, it's actually 100 years since Michael Bond was born, and he was also born in Newbury, strangely enough. But I think he spent most of his life in Reading, and then seeing the trains go in from Reading up into Paddington. Anyway, my kids preferred the Paddington one, and this was before the damage was done that made it onto national news. Anyway, back to the history of astrometry. So in terms of Gaia's USP and what it does best, that's measuring parallax. So I'll describe what parallax is in the next view graph. But the first parallax to be measured was in 1838 by the German Bessel. So parallax is illustrated here. So as Gaia or the Earth goes around the sun, it looks at a star, and then 6 months later, when it's halfway around its orbit, it looks at the same star, and that star appears to have moved in the sky. So that's what we're seeing on the left-hand side. And so we want to know the most difficult measurement to make in astronomy is distance. And so that distance is the dashed line between the sun and the star. And we know the distance between the Earth and the sun, so 1 astronomical unit of its Gaia. We actually track Gaia very carefully to know its three-dimensional position in the solar system, so we know that distance of the baseline very well. So then Gaia effectively measures that angle, and then with a bit of maybe GCSE trigonometry, I guess, then you know if you've got an angle and one distance, then you know the other side of the triangle, and that's how you get the distance to the star. So this is illustrated in the little movie on the right-hand side. So that's Gaia going around the sun at the bottom, and then the red line is the line of sight between Gaia and a star. So at the moment, that star is quite close to the sun. If you move it away, if you look at the top panel, the angle that it moves against the background stars is much smaller. So now the star's closer, and you see in the top panel, you're getting a much larger angle. And then as the star moves away, you're getting a much smaller angle. So Bessel, back in 1838, was able to measure the parallax of some of the closest stars to the sun because that angle changed sufficiently that looking through the Earth's atmosphere and with the telescopes at the time, he could measure that angle and therefore get the distance and therefore start to get an appreciation of the size of the universe, which obviously suddenly increased when he realized the distances involved to the stars. But as you want to measure more and more stars, then the blurring effects of the Earth's atmosphere are going to limit you, and so you're going to want to go into space and have some funky engineering to help you out. So then the next stop in our plot here, so the first space mission to measure astrometry was called Hipparcos. I've forgotten to put the acronym there, but you can see it's kind of like a forced kind of acronym from Hipparcos, the Greek astronomer. So this measured the parallaxes of 120,000 stars. So this was revolutionary at the time. This was launched in 1989 and operated till 1993. And so I remember using Hipparcos data during my PhD, which was more years ago now than I care to admit to. But Hipparcos is actually still up there. And I actually set the challenge to Guildford Astronomical Society to see if they could see it. I maybe didn't give particularly great coordinates, but you can see that Colin managed to see it. So in the bottom one, it's a bit easier to see. So all the solid lines are stars trailing, and then this is all the images of the Hipparcos satellite, like this kind of snail-like trail at the bottom, and then keeping the image fixed on stars, then you can see a faint trail of Hipparcos there. And then as Richard alluded to, I will show more pictures of satellites being seen by your members later. So then the final bit of the story in this particular plot is Gaia. So having built on the success of Hipparcos, so Hipparcos was a European Space Agency mission. Gaia was also a European Space Agency mission. We wanted to measure the distances to many more stars. So 120,000 stars is not many when the Milky Way consists of about 400 billion stars. Even Gaia, trying to measure 1 billion stars, is only measuring, well, actually Gaia can now measure about 2 billion. It's still a very small fraction. But the ability of Gaia to be able to measure smaller and smaller angles, as evidenced on the y-axis here, means that Gaia's, the volume that Gaia can measure distances for is much larger, and so we get a much better appreciation of the structure of the Milky Way and also how those stars move. And so that was the motivation for pushing down in this plot to go to space. But of course, we need a very good bit of engineering kit and a lot of clever software to do this. So it's a bit difficult to explain what that small fraction of an arc second means. So the analogy is that if you have, I think this is Buzz Aldrin standing on the moon. So if Gaia was at the Earth and looking at Buzz Aldrin's thumbnail, it would be able to measure the angle that Buzz Aldrin's thumbnail is seeing from Earth. So that's basically, and that's the number in degrees there. So that was effectively the challenge that the astronomers were setting to the engineers for Gaia. And that was the aim. So Gaia's actually not quite reached what we call micro arc second accuracy, but it's done extremely well. It's about an order of a few larger than that, up to 10 maybe micro arc seconds. So maybe it's getting kind of Buzz Aldrin's kind of hand now, as opposed to a thumbnail, which is still pretty good going, I think. And so it's, orders of magnitude better than Hipparcos in pretty much every statistic you could imagine. So how do you do this? Well, you need the biggest digital camera that's ever been made. So at the time of Gaia's preparation, it was the largest digital camera that had ever been put together, either on ground or in space. I have a slide later on that explains that is no longer true, but at the time, pre-launch, it was. So it's got nearly 1 billion pixels. And so Gaia likes the number 1 billion. So we've got nearly 1 billion pixels. We're aiming to measure 1 billion stars, and it costs about €1 billion. And it's been estimated that maybe you've contributed about €1 personally to the mission. So that's why I'm here to say thank you very much. So this is very much your mission. As Richard was saying, I'm from the Mullard Space Science Laboratory. Many of you have brought your fantastic telescopes to set up on the lawn there for various observing evenings. It's a wonderful place, and we should have more observing evenings like that, and I'm sorry that we don't. But part of this presentation is saying sorry why we haven't and why I've been distracted with other things. So part of the reason that I'm able to be here representing MSSL and talking about Gaia is that Gaia won the contract to test all these digital cameras. So that focal plane array with nearly 1 billion pixels is broken up into different CCD cameras, so charge coupled devices. So one of them is seen in here. So the little blue square, I can't get my mouse to work, but so there's 4 positions within this vacuum chamber. So that top bit kind of will get lowered down, and then the air pumps out, and then we can test the digital camera. But so these are Gaia's eyes, but the eyes actually need a brain, and the brain is the electronics box, which is on the other side of this vacuum chamber. And because those two parts were made by different manufacturers, so the digital camera, the CCD, was made by a company called E2V, now known as Teledyne E2V. So they're based in Chelmsford. They used to be a British company. Teledyne is an American company, and since the last spoken to, they've been bought out by the American company, although the Chelmsford site still exists and is still producing detectors for various missions. The electronics box, the electronics box on the back was built by a company called Sara in Italy, and so MSSL had the contract to test all 106 flight CCDs and many spares as well, and to make sure that everything operated okay. So the eyes and the brain would work together to produce essentially vision, and of course that mating was noted and then sent down to the spacecraft manufacturer, which was at the time called Astrium, now known as Airbus Defence and Space, and that was in Toulouse. And so actually when I first arrived at MSSL, I kept on seeing crates of in the foyer of these CCDs having just arrived or just being about to be sent off. And so the whole process took 5 years because we were only testing 4 at a time. So this is a movie to show the launch and also allow me to have a drink. So this is the satellite itself. So the sun shield is about 10 meters in diameter, and the turret's about 3 meters high. So this is its final assembly in Europe's spaceport, which is in French Guiana in South America. So it was launched on a Soyuz rocket, and the Soyuz frigate is what it's sitting on, like the lighter gold bit there with the sun shield folded up. Of course, the most important bit is what you paint on the fairing on the outside. So we've got a girl waving goodbye to Gaia as it goes. So if you recognize the kind of shape of the rocket, then you'd be right to do so. So it's the same kind of heritage of rocket, the Soyuz rocket that launched Yuri Gagarin, Helen Sharman, Tim Peake. Not exactly the same one, but all looking pretty similar. So if it ain't broke, don't fix it. And so this was in December 2013. So the video is a little bit misleading in that it looks like you've got technicians running around at the last minute just before it launches. So if we had sound, you'd be able to hear a countdown already starting now. And so it was a nighttime launch, so I was fortunate enough to be there. I never saw the shuttle launch, and in fact, I was hoping the sound was going to be a bit like what I've heard the shuttle one is like, but in actual fact, the sound of the launch was louder on the tannoy than what we actually heard in real life as it came to us, obviously with a bit of a delay. And so that's the various buildings that we were in to watch the launch. And then this is my selfie with Gaia. Fortunately, so a colleague of mine took a picture, and I thought she was being very annoying at the time. She said, "George, you know, just stay there." I was like, "What? This is like, you know, an amazing moment. Stop talking to me." But I'm very glad she kind of took the photo because Gaia is pretty much in space at that point over the South Atlantic, going ridiculously fast. So the next movie is all animations illustrating where Gaia was going after launch. So from our viewpoint down on the coast, we were able to see 4 little sparkles, and those were these side rockets falling off. So when the fairing came off, that was too high for us to see. And then, so this is the Soyuz frigate saying goodbye to Gaia, and then off it goes. So it went a couple of times around the Earth before doing that. And then a critical moment is opening up the sun shield, not quite as critical as for James Webb, but still pretty critical. And so then Gaia started spinning, and then so it spins once every 6 hours. And then it performs what's called a Lissajous orbit around a point in space called L2. So this Lagrange point 2 is a gravitational saddle point between the Earth and the Sun. So it means it's actually being dragged around the Sun by the gravity of the Sun and the Earth together. But of course, if you stay exactly in that point, you're in shadow, so you need to orbit that point, and Gaia orbited it with quite a close orbit around L2. And then this is Gaia. That was Gaia spinning and showing you that it's actually got 2 rectangular telescopes, so it's not firing out rectangular laser beams into space, as that video suggests. Is actually, that was just to illustrate that the light it receives. So what do we actually want Gaia to give us in terms of measurements? So I've described the parallax. So that gives us we measure the parallax by measuring the position of the star as a function of time. But also, as you're naturally measuring the position of the star, you actually get the motion in the plane of the sky. So that's the arrow coming down. So this transverse velocity. And so if you know the distance, you can actually make that into a physical velocity in kilometers per second. But what you really want is the space velocity, so how the star is moving 3-dimensionally in space. And so the other component that you need to measure, to having measured the tangential velocity in the plane of the sky, you need to measure the radial velocity in the line of sight. And then if you do that, then you can obtain the space velocity. So how do we measure the radial velocity? So this is illustrated by Pink Floyd here. So as you, I expect, know very well, if you have white light going through a prism, it's dispersed into its constituent colors. So this is the Gaia version of the prism that was used in the Gaia's radial velocity spectrometer. Then we had all sorts of optics on the left-hand side, and then so that was selecting the red part of the just outside the visible spectrum, in fact, and then onto the 12 CCDs at the end, so the 12 detectors at the end. And so that makes up the radial velocity spectrometer. So my day job for the last 15 years at least has been calibrating these detectors and then to measure the radial velocities from them. So basically we're projecting effectively star rainbows onto these cameras and then measuring them. So this is what these star rainbows look like. So at the top, so say we have flux on the y-axis against wavelength on the x-axis. So the top is what we call the continuum. So this is would be the constituent colors of the rainbow that you saw in the previous plot. If you digitize the counts associated with those, then you can see you have these absorption features. So these appear as dark bands in the star rainbow, and they form very particular patterns. So in particular, the radial velocity spectrometer is centered on what's called the calcium triplet, indicated by the Ca lines there. So there are 3 lines caused by calcium atoms, which are actually ions in the star's atmosphere. And those ions are blocking light from getting to us. And so it's an absence of light at these particular wavelengths that cause these troughs in the spectrum. And because we know where those troughs should be, we can measure the radial velocity from that. So this was just to illustrate the wavelength range. So the wavelength range is it's actually 850 nanometers. In fact, so that's actually just outside the red end of your that your eye can see. So your eye can see between 400 and 700 nanometers. And just to be confusing, astronomers have a slightly different axis on this one. So this is angstroms, but this is effectively just 10 times more. So this is about 850 nanometers. And then because we know where these lines, these absorption features should be, we can see when a star is at rest. And then we also know if the star is moving away from us. So we know this from laboratory measurements. And then so by looking at the spectrum, so having calibrated our x-axis, we can see if a spectrum is shifted to the red end, so that's moving away from us, or a redshift, or whether the star's moving towards us, or the light's being blue shifted. So when I say redshift, I actually mean this is really a physical motion of the star towards us, as opposed to a cosmological redshift, which you'll probably hear about next month, I think, from your speaker.
Yeah.
So this is actually how the star is actually moving away or towards us, a bit like the ambulance siren with the Doppler effect with sound. So there we go. So we can measure, we can measure these very small shifts to actually get the physical velocity of each star. So then I'll come to another historical coincidence. So I did my PhD in measuring radial velocities. So if you were here back in 2017, you might remember this. But so when I started my PhD, I never checked my whether I'd published any papers, because I knew I hadn't. But one of my colleagues had, and said there was someone with my name measuring radial velocities, so motions of spectroscopic observations of stars in the line of sight, about 150 years ago. And so it actually turned out, following up on this, I found out it's actually my great-great-grandfather, who's got nearly the same name as me. So I'm George Michael Seabroke, and he's George Mitchell Seabroke. I don't sport such an excellent moustache as his.
No, I can see it.
You can see, but maybe you can see the ears, I think. And yeah. So this was a great surprise, actually, because we had no idea. I think there was a rumor in the family that someone was interested in astronomy, but then that doesn't really explain this. So it turns out he was a solicitor by day and an amateur astronomer by night. So he made all these measurements. So I had before I get to that bit. So but actually before he started measuring radial velocities, so doing a bit of research on him, I found that he was connected to Edward Maunder, which is a name you may or may not be familiar with. So if you may have heard his name from the Maunder minimum. So this is from so the plot at the top has got year on the x-axis and the number of sunspots on the y-axis. So this is what the Royal Observatory Greenwich used to do, is to count how many sunspots there were, and so he analysed this data a bit later in his career and found out that the number of sunspots was very small back in the early period of when they started doing those measurements, and it was named after him as the Maunder minimum. But before he did that, so when he first arrived in Greenwich in 1873, I think it was. So so this was at the very early stages of when astronomy, so classical traditional positional astronomy, so very much what we're talking about with Gaia, was becoming astrophysics. So people were using spectroscopes to split up the light, as I've just described. And he was actually, so one of the first things he did upon entering Greenwich Observatory was go down to Rugby to see Mr. Seabroke, who met on the previous slide, to give him some lessons of a particular form of spectroscope which Mr. Seabroke had devised. So I think this spectroscope was a one for observing the sun and actually trying to find prominences on the sun. And so I don't think I couldn't find any evidence of Maunder ever taking his particular type of spectroscope and using it at Greenwich. But there was a bit of knowledge exchange in the opposite direction, because Maunder was measuring radial velocities before Seabroke, and then I just come back here. So he started in about 1874, I think it was, and then George followed him in making these measurements. So I had a summer student digitize these numbers and compare them to Gaia measurements, and on the y-axis is the radial velocity in kilometers per second, and then the year of observation on the x-axis. So apologies for the color coding is a little bit. And I've not very helpfully covered up some of the some of the legend, but basically George Mitchell Seabroke's measurements are in dark green, and so you can see for this star, this particular star Gamma Cygni, which is a naked eye star that you can see, part of the Swan constellation. He measures it both to be moving quite fast away from us, and then a few years later to be coming towards us very quickly. And we know from Gaia that, of course, stars can do this, and we'll come to a bit later in the talk. I'll show you some examples of interesting stars doing this. But we know from Gaia, so although the Gaia measurements aren't contemporaneous with their measurements, we know that this star doesn't vary with radial velocity. And so these are very large measurement errors. And you can see that Maunder, with the lighter green and the blue, with his measurements, he was doing slightly better, but still a very large scatter. So the reason was they were using a micrometer and trying to measure radial velocities by eye by dispersing the light and then comparing it to an arc lamp and a spark as a reference point. And so this was ambitious. So people were successfully measuring radial velocities, but really the accuracy only came when photography was introduced. And that happens about towards the end of this plot here, when they both stop, when people are measuring radial velocities much better from photographs. And so both George Mitchell Seabroke and Edward Maunder stopped their visual radial velocity programs, and nobody's ever done it since, because it's unfortunately a waste of time. But I'm glad to say, so that was, so it's good news that he stopped, but he did also make visual measurements of double stars. So double stars are when you can actually see both components of a star and they're going around each other. But of course, we're seeing the complete orbit of these two stars around each other. And this can take hundreds of years, in fact. So double star observers, and there may be some in the audience, people still do this for fun. If you take a double star measurement, then you don't necessarily know that it is a double star, whether it's a physical binary or just a chance alignment. And it's only taking measurements over many years will it reveal its true nature. So he actually did this. So the sorts of measurements that you'd make are here. So you have your brighter primary star A in the middle, and then you're basically measuring the separation to the secondary star B there in arc seconds, and then a position angle in degrees. And so he actually made, so on the left-hand side, he actually made quite a few measurements of those. So it's about 2,000 in total, and they're all in the Washington double star catalogue, along with Maunder and Greenwich also did this, along with many other people. And so these measurements are actually useful, because for some stars, to say their orbital period can be hundreds of years, and so this was a useful use of his time. So that was good. Maybe not good for his family, because I don't know when he ever went home, because he seemed to be at the observatory every night. So in taking these double star measurements, one particular bright star is this one. So we can't really see what's going on very well. This is from a photographic plate that's been scanned, and so the middle here is being saturated. So I'm just using it for illustrations purposes. So in the middle, we've got a double star. So we've got an A and a B component. And so these are the Washington double star catalogue measurements at the top here. And so some of the more errant ones are George Mitchell's, but they still are, you can still see that they are sort of broadly consistent with this orbit that you're trying to measure over time. So Gaia didn't actually, so of course, if you can measure, this is a very bright star, so Gaia is actually struggling at the moment to measure very bright stars, but you can still measure them visually. So this was actually one, at the moment, until at least, until the 2nd of December, when Gaia's 4th data release is gonna come out, you can visually do better than Gaia, in that Gaia can't actually measure either of these components, but not yet anyway. And then, so it turned out that George Mitchell was the first to measure some other components that Gaia also misses. So the stars, so he measured the distance and the angle between A and C and A and D. So he did that because he thought maybe these stars are all physically related. So it turns out that they're not, but of course you don't know that when you're taking the measurement. And at the moment, Gaia hasn't seen those, but it may or may not have seen them in the fourth data release. So I'll have to come back and tell you if it's actually seen those. So basically, Gaia's struggles with very bright stars and how it processes very bright stars has been improved quite a lot over the years. So he did this work with this telescope here. So it's an 1859 Alvin Clark telescope, so 8¼ inch. So this is quite an early example of Alvin Clark's telescope. So nearly every university in the States has got an Alvin Clark telescope, typically later than this one. And it was, I think this one actually, that really helped Alvin Clark, so the US manufacturer of these telescopes, to make a name for himself, because he came over with several of these and sold them to William Dawes, who was a famous double star observer in the 19th century. And he thought they were very good and discovered lots of double stars with this telescope. And so he went back to the States and people started buying them after that. So the telescope actually belongs to Rugby School, so it's called the Temple Observatory. And the observatory building was, it's got a sort of interesting dome there. So that was built in 1877. So it'll be its 150th anniversary next year. So we're hoping to get the telescope fixed. So it needs mechanical and work and cleaning. So we're trying to do that with these, someone at MSSL and someone from main UCL to get this fixed up. A bit like your heritage telescope that you're considering getting fixed up. This is also what we're trying to do here. So hopefully you can do yours, we can do ours, and we can get lots of public observing done. Although obviously you have to travel a bit for this one. But so yeah, I think so historically, I don't think there's another Alvin Clark telescope in the UK. So it's quite historically interesting from that regard. And optically, these were the best telescopes at the time. So we'd hopefully produce some lovely images for the public to look at. So this was my main excuse for not inviting you to MSSL more often, because I've been trying to get this project up and running. Anyway, that was a bit of a going off at a tangent. Back to Gaia, but there is a segue now from from ancient double star observations to binary star observations that Gaia can make. So Gaia, as we say, was measuring the positions of stars as a function of time, and it's doing that incredibly accurately. And so this has actually allowed us to start discovering a new type of object, and these are dormant black holes. So I'm sure you would have heard of and probably had talks about supermassive black holes. So the types of black holes that have got millions or even billions of solar masses living at the center of our galaxy. So our particular supermassive black hole has got millions of solar masses. Larger galaxies, they've got billions. But what Gaia has found is dormant stellar mass black holes. So you can see from the masses here, so Gaia black hole 1 and 2 have got similar masses, so 10 and 9 solar masses. So these are from left over from stellar evolution. So we're not really sure if they've formed from two smaller black holes merging together, giving out gravitational waves and then producing these a merged black hole, or whether they're formed from a single star collapsing. So the first two black holes were discovered, they were very kindly named after Gaia, but they were actually discovered by people outside of the collaboration. So the various filtering and quality assurance from the data that we did meant that we actually missed them. But Gaia Black Hole 3 was actually discovered by the collaboration, and itself is a record breaker. So it's 33 solar masses, and let me show you how we discovered it. So on the left-hand side is a very small patch of sky, and we have a star going around a particular point. So Gaia was taking all these positional measurements, and we can see that it suddenly speeds up and then slows down, And so it speeds up because of the gravity of the black hole that resides at this point called near periastron. So we're calling them dormant black holes because they're not actually emitting any light. There's no evidence that there's anything there other than the motion of the luminous body, so this other star that we can see. Oops, sorry. Let me come back and set that going again. Sorry. Where's my thing? There we go. Okay, so on the left-hand side, as I say, is the astrometry. So that's the measuring the stars, measuring this star as a position of time, as a function of time. On the right-hand side is the radial velocity. So the radial velocity on the y-axis against time on the x-axis. So you can see it's quite a different plot, but it kind of fits in that you basically you can always have a problem with one or other, but with both parts of the independent measurements suggesting that you've got a very massive object that you can't see, then you're confident that you've discovered something interesting. And so because of the radial velocities there, I was fortunate enough to be involved with that. And so this puts the black hole 3 discovery in a bit more context. On the y-axis, we've got the black hole mass against orbital period on the x-axis. So most stellar mass black holes prior to Gaia are discovered in X-ray binaries. So this is when you've got your black hole and a star that's sufficiently close to the black hole that the gravity from the black hole is ripping material off the star and it's spiraling into the black hole in what's called an accretion disk. And as it gets really close to the black hole, it gets heated up sufficiently that it produces X-rays. And so we can see those X-rays. And that's how we discovered most of these black holes. So with Gaia, these are a different way of doing it. As I say, this is doing it astrometrically and spectroscopically. And then you can see the Gaia black hole 3 is really an outlier in terms that it's got a very long orbital period, which means it's very far from the luminous partner that it has, that it's going around. And it's also much more massive than all the other ones that we've found. And so this is interesting from how this fits into gravitational wave astronomy and all the interesting results that are coming out of that, and how this can be understood in terms of stellar evolution. And of course, it does make for good headlines as well. So, of course, so the best one was from the Metro, and of course, starting off with potholes and then saying, at least they're not this big. Although you may have potholes near you that are actually that big. But, yeah, so that was fun. And then also, so we've shown how the Gaia's measurements as a function of time were used to discover it, but also Gaia's measurements, like the measurements I was talking about before, so the time average measurements can also give us context for what this black hole is doing. So at the top, it's a repeat of the plot I was showing before. So we can work out from Gaia's measurements how fast the star is moving in the plane of the sky, and also the radial velocity. So if you put those together, you have the space velocity, and if you have the space velocity and you make a guess at the gravitational potential within which the galaxy basically sits in, then you can calculate orbits of how this star is actually orbiting around the center of the galaxy. And so that's what you're seeing in the bottom left plot. And then the plots on the right are in sort of technical units, but in effect, they are angular momentum in one axis and angular momentum in another axis. So what we can see is that so Gaia black hole 3 is the red cross. So you can see it's consistent with a stream of stars, which have been called ED2 after the author, but I can't remember her name now. And this stream of stars, which clump together in different ways, depending on how you plot it, is thought to be a globular cluster, so a cluster of stars that were born together which have since been ripped apart by the gravity in the Milky Way. But because the velocities effectively remember where or they have memory of or they have a shared property, you can trace this back to, you can see which stars belong to which cluster. So that's effectively what we're seeing in the plot here. And so we think that Gaia Black Hole 3 formed in a cluster, and so that's interesting. So that could be that you have very dense environments in the center of globular clusters in particular, and so you could have the scenario where you have lots of binaries interacting together to form this system. So this is and then also you have the metallicity. So basically the chemistry of the stars can also be put into this argument as well. So this is an area of ongoing research. So you can also use Gaia's very accurate positions to do more than just see how stars are moving. So this is how a star moves. So it's quite an old slide now, but you can see, so this is a very small patch on the sky. So the dotted line is how well, and the solid line actually shows how the star actually moves as a function of time in the plane of the sky. So let me illustrate that a bit better. So the turn back as a function of time is the effect of the parallax. So that's Earth's orbital motion around the sun. So if the sun, if this particular system wasn't moving in space, then you'd just see this ellipse going around and around. But because it is actually, it's got a motion in the plane of the sky, that ellipse gets stretched out into this helical shape. So that's illustrated here. So if you actually, if you looked at this, how this star was moving from the center of the solar system, then you wouldn't get this helical shape. You just get the dashed line in the middle. So that's really what we're after. And then the dotted line is how a well-behaved star would move. But the solid line is how a star moves if it's got a planet going around it with sufficient mass that it actually perturbs the position of its parent star. So Gaia's astrometry is sufficiently good, although it's been magnified 30 times in this plot for visibility, but the positional accuracy of Gaia is sufficiently good to actually see effectively Jupiter's going around other stars and making the star position wobble. And so this is the astrometric method of detecting exosolar planets. And so over a while back, it was predicted that Gaia was going to actually measure 71,000 planets in its full mission data set. So we've got the full mission data set, but we're still analyzing the data. And it's actually, even within the Gaia collaboration, it's a bit of a secret. I don't actually know how many planets they're going to tell us that they've found. So I'm quite excited to hear about that. So for context, as of I think that's the typo actually. As of yesterday, we know of about 8,000 planets, and so the number of planets that Gaia could discover via the astrometry method, it could really be a game changer. So it has already discovered some planets. So back in April 2003, it actually combined the astrometry from Hipparcos, which you heard about earlier, and Gaia, but it cheated a little bit in that it used a telescope in Hawaii as well with some direct imaging. And with those three measurements, it was able to discover a planet. So it hadn't quite discovered its very own planet all by itself at that point. But this movie will illustrate that it has now discovered its own. And I'll have a drink. So it's basically saying what I've just said, but maybe slightly more eloquently. And in some ways, I don't like this movie because, you never have planets leaving a streak like that. But So the first was a planet, but the second one is a brown dwarf that it's found. And so I think there'd be some dreamy music if I had the sound working for this. So that's some exciting things to look forward to. So then Gaia sadly came to the end of its mission. So having been launched in December 2013, it started its nominal mission of data taking in July of 2014 after commissioning. And then on the 15th of January last year, it made its last science observation. And so these are some of the incredible stats that it's accumulated along the way. I won't go through all of it. Some of it we've already talked about, but the 3 trillion observations of 2 billion stars is fairly impressive. And so we're still trying to process all this data. And so I'll be trying to convince the UK Space Agency to give me some more money to do this actually on Tuesday. So after the 15th of January, with the end of the nominal mission, they wanted to, Gaia had a few issues, which I haven't talked about, and the engineers who built Gaia wanted to do some experiments to understand what had happened to Gaia, so that it could be a lessons learned exercise for when they make future spacecraft. And so Gaia Gaia's sunshield was tilted towards Earth, typically that it was very faint. And so it was actually, if you were to try and observe it through a telescope on Earth, it was about as faint as the stars itself it was trying to measure. You see what I mean? So that was about 21st magnitude or so. So effectively, millions of times fainter than what your eye can see. But with the engineering test they wanted to do, this actually involved tilting Gaia's angle to the Earth, so it was more kind of face on, and so this actually made Gaia become a lot brighter, so about 15th magnitude or so, and this was so this allowed these engineering tests to happen, but it also allowed observers like yourselves to get involved, and so I encouraged you to try and take some images and movies of Gaia. So this is Colin's movie of Gaia. So it's performing an S shape there, and then you probably know which image is coming up next. I see Tim smiling. So it's probably what I imagine is a very famous image in this group now. I certainly hope it is anyway, because it's a wonderful image. So this was by Tim, effectively tracking, taking different snapshots of the movie that Colin had, but you really see this S shape here. And so Tim came and gave a wonderful talk on why this happens, and you can ask him why. I can't remember either. But he did it. Yeah, but it's all very very well explained when he came, and so I got him and some of the rest of you to come with your telescopes, and we did a farewell to Gaia in its final weeks to celebrate this image and to do a bit of observing. The idea was to try and see Gaia itself, but I think that was a bit ambitious at the eyepiece. So I think it was at the end of that week, actually, when we'd had that event, that the actual final switch off happened. So then I was fortunate enough to go to the European Space Operations Center to see the end of Gaia. So this is the focal plane here that I showed you before, that's slightly inverted. So this is now the engineers involved switching off each detector one by one. So the numbers you're seeing there are the voltages that they're passing to the electronics. So then it became apparent that in actual fact, this wasn't a random sequence of turning off, And people started to think this might be something happening. And, and indeed, so Gaia finally said goodbye. And that actually brought a tear to many people's eyes in the room. And then that was it. So after that, there was Gaia was effectively safely decommissioned, and as I think you'll probably hear next time, there were lots of other missions at L2. So James Webb being the most expensive, and so Gaia was now then sent away from L2, so not to cause any traffic jams up there. So as we speak, Gaia is no longer operational, but it's still the largest digital camera in space. So you may have heard of Euclid, and hopefully you've had a talk from someone at MSSL about Euclid. So if not, I would recommend doing so, because Euclid is producing wonderful images of galaxies. It's a cosmology mission. So that's got 600 million, 0.6 billion pixels in its camera. So it's operational, but Gaia remains the largest digital camera in space at the moment. So until early next year, when Plato will be launched. So Plato will become the largest focal plane in space. So that'll be 2 billion pixels, and I'll be working on Plato and helping to commission all of those 2.1 billion pixels next year, which is a bit scary. But all of these pale into insignificance. So the largest digital camera, either on ground or in space, is the Vera C. Rubin Observatory in the States, and that's got 3.2 billion pixels. Yeah, so that's just to put, if you're a sizist in terms of your digital camera, to put it in context. So this movie will show you where Gaia is. So I think it's quite long, so I'll have a drink. So I think it's going to tell us some of the things that we've already seen. So this is the Lizard-U orbit that you saw some loops of at the beginning. So that's how it traces out its motion in space. Oh yeah, so basically we would have kept Gaia going if we could, but we effectively ran out of gas. And so that was the limiting factor. So we had to save enough gas in order to boost ourselves away from this Lagrange point 2 into its retirement orbit. So now we see, yes, so now we see, so the Earth's going around, and you see that Gaia is no longer following the Earth. It used to be in line with the Earth, but now it's lagging behind more and more. And so I think Gaia is probably too faint to be seen already. But if you want to put a date in your calendar, so in 2039, that lag will mean that we'll actually catch up with Gaia again, and so that'll be the next time to try and take an image of it. So I'm hoping the society will rise to the challenge there and start planning your observations. So the mission isn't over. So there's lots of data processing to be done still, but there's also ways in which you can be involved. So there's you can't really call yourself a big project these days if you don't have a project on the Zooniverse, so a citizen science project, and Gaia does. So it's so it actually uses the photometry in Gaia. So that's the measurement of the brightness of stars. So I haven't really said much about this, but Gaia stars actually change their brightness in particular ways. So in this particular example, I think this is a Cepheid variable. So if you look at the top plot, that's the brightness of the star as a function of time. which looks a bit disorganized, but if you know the period on which that variation occurs, and the process called folding on the periods, then you get a much nicer pattern at the bottom there. And so the idea so Gaia's asking, so apparently the machine learning that goes into finding all the different patterns that can be in these stars is still not sufficiently good to find all the unusual examples. And so the idea here is that you can help actually classify stars that Gaia has observed on the Citizen Science, the Zooniverse platform. And then there's some plots on the right-hand side that give a bit of context to each star. So if you're at a loose end, I'd recommend starting to work your way through all 2 billion of these. I happen to know that if you spend 1 second on each, it will take you about 30 years to get through them all. So good luck. I don't recommend that. But having a look at 1 or 2 might be fun. So I've talked about Gaia. So its primary science goal is to survey the Milky Way. But in doing so, it has to look through the solar system. And Gaia was designed to measure anything that looks like a point source. The most numerous of those being stars. The next most numerous of those being the cores of galaxies. So Gaia's actually seen millions of galaxies as well. And then the next most numerous after those are asteroids. So it's actually seen 150,000 asteroids. And so most of these asteroids are already known. So the number, I don't think there's not really many at all that are new. But with asteroids, their orbits don't tend to be particularly well known. They tend to be observed and then lost. And so finding them again and measuring and getting new positions to improve their orbits is very beneficial. And so that's what Gaia's been doing. And then we have the interesting scenario of asteroids having their own moons. And so Gaia's also been discovering hundreds of these systems where you have a moon going around an asteroid. But of course, the way Gaia scans means that it just sees a snapshot of these measurements and then it will see it again, but you can't go back to point at it exactly when you want to in terms of its orbital motion to get the exact measurements that you want. And so there is a way of actually being involved with doing some observing from the ground and helping with this. And so this is called Gaia Moons. So it uses occultation. So that's when one of these asteroids passes in front of a star. So Gaia knows the positions of these stars very accurately. Hopefully that's one of the main messages you remember from this talk, that Gaia can measure stars very accurately. And so so we know where the star is, and then as the asteroid passes in front of the star, if you can time when the star light dips and how it dips, and you get lots of people doing that from all sorts of different directions, then you can work out whether that asteroid has got a moon. And so they're asking people to do this. So this is another observing challenge that I'm setting for you, although it's quite challenging. So you have to sign up to this and get notifications. But of course, unless you've got a portable telescope and you're willing to travel, the path of the occultation may not be anywhere near you. So you might have to be quite keen or patient and waiting for one that might come by. The other challenge is that some of these timings can be quite short. About the longest I've seen is about 10 seconds, which might be within the sort of range that you can manage, but some of them are less than a second. So being able to read out your detector that quickly is maybe a job for CMOS, which is another talk. So that's a different imaging technology to the one that Gaia has. But anyway, that's if you're feeling like you haven't been sufficiently challenged, then I'd recommend, if you're an observing project, this could be it. And then, so there is still the possibility that within Gaia data, it can save our lives in 2 different ways. So there are because of its vantage point at L2, you can see that so from the Earth, you've got the nighttime sky, which is when most of the observing of asteroids occurs. But Gaia's vantage point can actually see closer to the sun, so it can actually see near-Earth asteroids for longer. And so there is still the potential that in the data, there is a near-Earth asteroid in there that we can actually get some more measurements for its orbit, and it could be one that could potentially ruin our day and come and hit Earth. Potentially, I'm not really sure of the chances of that, but there is still the potential that Gaia could save your life. On the right-hand side here, some of the techniques of mapping the stars have actually been applied to how to map cancer cells. So this is a collaboration in Cambridge with the Institute of Cancer, and so some of the technology has been transferred over, and so that could be another way that Gaia might save your life. So, so this is a graphic for Gaia's last data release, which was back in 2022. So I haven't talked about lots of aspects of this. Hopefully you can recognize some that I have talked about. So nearly all of these observations, the Gaia collaboration have been processing the data and aggregating them and averaging them in sometimes simple ways, sometimes complex ways, but it typically would be a measurement that is constant with time. And it's done that for these 1.8 billion stars. But the next data release, which is coming out in December, it's doing that again for all of these properties of the stars. It'll be improving those because we have more measurements. We're improving the calibrations, and so the systematics and the accuracy of all these measurements are improving. But we're also releasing all the epoch measurements. So every measurement that's actually gone into the aggregated measurement is also being made public. And so we're basically, so each star has been seen maybe 100 times, and so we're measuring every observation of that star. So 1.8 billion stars with 100 measurements and many different aspects of all those measurements. So all of that is coming out on the 2nd of December. And just to illustrate, hopefully, that what the impact that will have, on the y-axis here is the publications by year, and on the x-axis is the year. So you can see the Hubble Space Telescope was the European Space Agency's, and in fact everybody's most scientifically productive mission, until Gaia came along. So Gaia's in the red, and the purple lines are or the magenta lines are the Gaia data releases. So when I came and gave you a talk in 2017, Gaia was still just getting going. So since then it's more than so it's basically about 4 papers a day coming out using Gaia data roughly, which means that it's more than twice as productive as the Hubble Space Telescope. So you can tell I'm practicing my pitch for why we should be funded next week. But you can see we're kind of tailing off a bit there. And so maybe when we release all the epoch data to allow the community to actually reanalyze how we've done things within the collaboration, then hopefully we'll see another step change there. But anyway, hopefully it's been value your €1 contributing to this mission and contributing to my dinner tonight. So thank you very much. Hopefully you agree it's been well spent, but the mission isn't. The operations are over, but the data processing is not. So maybe I didn't say that the data release that's coming out this year is the first 5.5 years, and then the final mission data will come out in 2030 something, and that will be the full 10.5 years. So you'd be pleased to know you've made it to the end. This is my final slide. So, so hopefully I've convinced you the Gaia revolution is in full flow and it's not finished yet. So we've got our next data release is, actually I could have updated that. So we know that's now December the 2nd this year. So it could be a revolution in the number of dormant black holes that it finds, and also in the number of exoplanets. And then the final data release is going to be in the 2030s. So when I came and gave you a talk back in 2017, there were various ways of following up Gaia. So there were photometric alerts. So this was when a supernova goes off and when Gaia would observe it, they would send out an alert for it to be followed up. So this is why light curves of supernovae tend to die away within a month, and Gaia may not see that patch of the sky again in that time frame. And so that's why we were asking people to follow up. I don't know if anybody did, but of course that's over now. But you did very successfully follow up on the satellite itself. And you now have to wait till 2039 before you can do that again. But as I explained, you can. There are still observing projects to be involved with, and there's also the Zooniverse project if you'd like to get your hands dirty with the data. But that's all, folks. Thank you very much.
Thank you. Thank you very much, George. That was a really
sorry for going a bit over.
Fascinating talk, and obviously you can see the contributions from our group as well as your €1 that helped. So yeah, we'll take some questions. Does anybody have any questions for George? Oh, okay. I have to wander around with my mic.
So I wanted to know the spin that Gaia does during the orbit, the satellite itself spin, is that purely to just get a view of the that purely just to get a view of the night sky, or does the centrifugal forces the spin produces help the telescope in any way to gather the data or help the instruments operate?
Yeah, that's good. So that's a good question. Yeah, so both basically. So so it helps Gaia see the night sky. So if it just sat in its position in L2 going around, it would scan the sky, but not very quickly. So you can help speed that up if you spin and precess. So it's like a spinning top, kind of wobbling around like this around the sun, basically for the last 10 years. And then another reason for spinning is that, and actually another reason why it's not really a fair comparison with Hubble, because Hubble steps and stares. So it stares at a patch of sky for sometimes months and adds all that data up, and you see wonderful distant galaxies. Whereas Gaia is continually continually scanning and taking data. And so the spin actually helps you. If you have the right technology on board, you can be shifting position and collecting data at the same time. So the way the digital cameras on board work is that they collect the data in a particular pixel, and then, but as Gaia's moving, so as the image, so if Gaia's stationary and the image is moving over Gaia, then the digital camera clocks the image that it's received in this pixel at the same rate as the image moves over the camera. And so it accumulates signal as it's spinning. And so that enables it to be a much more efficient survey machine than it otherwise would be. So there's, hopefully that answers your question.
Cool. Thank you.
Thank you. Any other questions? Oh, Dan. Keep it. There you go.
You've mentioned the data drops a couple of times. Could you give us a sense of how the data gets from Gaia to Earth, and then what happens to it? Is it processed on Gaia first, then dumped down, and then processed?
Yes, good. Yeah, so I could have, I did have some slides on that, which I should took out. Yeah, so on board, so there's a little bit of data processing actually within the digital camera. So for most of the data, we take little windows around each star, effectively a sort of picture frame around each star, because most of space is black, and we don't need that, and we didn't have the technology on board to download all the data. So actually Euclid does and downloads massive full frame images, but it's got better telemetry technology on board. But so we didn't have that available to us, and also the data rate is just horrendous. And so you've got to reduce that. So you take little windows around each star, and so you dump all the black space around the star, and then you don't actually need what we call the acroscan direction of the star. You actually only need a profile in the direction of the scan for where the star is. If you see what I mean, I've got a pen to illustrate this. So you're kind of just having a profile of effectively a 1D profile of what the star looks like. So you can collapse the two-dimensional data on board. So that actually happens within the readout process of the detector. And then there's a lot of compression before telemetering it down to Earth. Then there's a lot of unpacking of that. And then in terms of processing, there's, so it all comes down to NASA's deep space network. So there's sort of radio dishes in Argentina, Australia, and Spain, and Goonhilly, actually, so in Cornwall. So that was a recent addition that didn't exist when Gaia launched, but actually when those three networks are effectively taken up, the bandwidth is taken up sometimes by other missions, sometimes just because Gaia's got so much data on board, because it's looking at the galactic plane, for example, then Goonhilly is a backup to receive more data. So then all of that data goes to the Madrid, so the European Space Astronomy Center, and that does all the unpacking, and then it distributes different parts of data to different centers. So the spectroscopic processing, so the radial velocity, star rainbow stuff that I do, that's all sent to the French Space Agency in Toulouse. So they've got a big supercomputer there. And basically my day job is working with software engineers to develop code that will run there to process all the data. And so then so that produces science products, and then that data gets sent back to Madrid, who then package it up, ready for the release, and then it goes into a big table.
And is that sort of petabytes or zettabytes, or is it less than that?
That is a good question. I'm glad I put this slide in, because I'm hoping this will. Oh. So yeah, we've got 142 terabytes of downlink data. It's compressed, and then 500 terabytes is what we're going to release in December, roughly, and that's half the mission so far. So yeah, there's still a long way to go in terms of data processing.
You got? Oops. Hello. I heard there could be talk of reclassifying Pluto as a planet.
Oh, I haven't heard actually,
Okay.
but yeah, I
don't know what I was listening to or something. I was listening to
don't
something
know.
on maybe radio or something about reclassifying it.
So I don't think so. Gaia can't really help with that, I would say.
No.
It did help with the New Horizons navigation, actually, to get to Pluto and beyond. So so I think NASA wanted some of the star positions. I guess maybe this is going back a few years now. So they knew that the Gaia collaboration had more accurate star positions than were in the public domain, and so they asked for those to be released to NASA to allow for improved navigation of the New Horizons probe to get there. So that's the only link I can make.
Do you think it deserves to become a planet again?
I don't know. I guess I've spent so long to getting used to being a dwarf planet.
Right. Yeah.
I mean, if you look at its orbit, it's quite it comes inside of Neptune's orbit and outside. So it hasn't. So the criteria of effectively sweeping up all the material in your orbit, it doesn't satisfy that criterion, because obviously Jupiter is part of crosses its orbit. So pass.
We'll take one more question before the break. Okay. Yes.
You distinguished between cosmological redshift and I don't know what to call it, redshift.
I guess,
classical redshift. But there isn't any difference in the results, is there?
Well,
if something is traveling away from the observer at 100 kilometers a second, it doesn't make any difference which of the two.
Yeah, I suppose we distinguish between the two as your physical interpretation of them. So the cosmological redshift is you're seeing the universe itself expanding. So the object itself isn't necessarily moving at that speed, but space itself is expanding and the object's going with it. So we call that cosmological redshift. Whereas in sort of a more of a classical sense of, an ambulance going by or a siren and a physical velocity of motion compared to you, then that's what Gaia is measuring. Yeah, so I mean, it's still the same process of still a cosmological redshift is measured from a galaxy spectrum, just in the same way as you measure a stellar radial velocity from a stellar spectrum. It's just that it's just the interpretation of what's causing that motion that causes us to. That's the distinction.
But for Gaia, there was no difference in the interpretation of the speed.
Gaia's measuring. Gaia can't see. In terms of spectra, we're not getting spectra of galaxies that are experiencing cosmological redshift. So we are getting. So typically, their redshift would be. They would have different features to stars, and they'd be redshifted out of our wavelength range. So in the radial velocity spectrometer, these objects typically would probably be thrown away. There are some lower resolution spectra of galaxies, but they're not high enough resolution, I think, to get the redshift for. So yeah, we're measuring stars predominantly, and all of those, and so basically the Milky Way, Andromeda, and the surrounding galaxies are like a bubble that are moving together in space. So all the motions that you see within that local group of galaxies, you can interpret as physical velocities, and then gravitationally altogether, they're experiencing the expansion, like the other galaxies in more distant.
Yeah. Say that if there's a cosmological redshift, it will get small close by a star. What the measurements wobble around that.
Yeah.
Sort of changing.
Yeah, I think you are still measuring the physical motion relative to you in that it is a sort of a gravitational effect, because basically there's no cosmological redshift you see with the galaxies within the local group. They're not on scales that experience the cosmological redshift. The scale is too small to see that. So yes, and I think it is effectively decoupled. You kind of your sort of gravitational potential well that all these galaxies exist within are being told how to move by the gravity of all these galaxies. Well, actually, it's all the dark matter halo surrounding all of these, and it's that dark matter halo itself that, as an entity, is within it is decoupled from the expansion of the universe, but it itself is part of that expansion.
Thank you.
That makes sense. Yeah.
All right.
So, yeah.
So thank you, James.